Hi, today we're going to talk about a new chapter, Chapter 2, and this is specifically Section 2.1, Relations and Functions. So we're getting into the functions part of algebra, which is one of my favorites. Relations and functions, we're going to be able to determine all functions are relations, but not all relations are functions. So functions are more specific than relations. Relations kind of or anything that we talk about where one thing is relating to another. Functions are very specific. We'll talk about domain and range, discrete versus continuous relations, graphing relations, independent versus dependent variables, function notation, and evaluating functions. So hold on tight, we got a lot of information here, so get your notepads ready. Okay, a lot of this is review. Domain and range. Okay, if we're talking about domain is every x input. All right, so every input into a function. So if we're looking down at this table down below, you can see the domain would be the inputs. That's what's going in. So if we put 1, 2, and 3 into some function, those would be all the inputs. Those are the domains. So that domain would be 1, 2, and 3. Okay. The range is the output of a function. So if you put a number into a function, what comes out of it, that gives you the range. The range is the y values. Okay, so it just tells you all the y values. All right, domain goes with the x's, range goes with the y's. So domain is with the independent variables and range is with the dependent variables. Functions. Okay, to have a function, definition of a function is for any input, there is at most one output. Or maybe another way to say that is for any input, there is a unique output. So if I had an x value go into a function, the most I would get out, it's possible to not get anything. Like if we put -2 into the square root function, well, you can't take the square root of a negative, so that wouldn't give us an output, but it's still a function. If we put in 2 square root function, so the square root of 2, we would get one output. There's not multiple answers there. Okay. Now if you did plus or minus the square root function, then if you put in the number 2, your output would be both, the square root of 2 and the square root of, or negative square root of 2. So that would be 2, so that wouldn't work. What that would kind of look like, as far as a graph goes, like I said before, we just had the square root of x. Square root of x has a curve like that. Okay, for any input, there's only one output. If we said, so that would be, this is y equals square root of x. Okay, if I changed it to y equals plus or minus the square root of x, alright, well then we have the positive outputs, but we also have the negative outputs. So that is not a function, that's a relationship, but it's not a function, or a relation, but not a function. Okay? A test that we have for that is called the vertical line test. So if I draw a vertical line there, it hits both here and here. Since it hit more than once, it is not a function. This one, I can draw a vertical line anywhere on here, even over here where it's not drawn. It only hits at most once. So definition of a function, where any input hits at most one output. Okay, your book talks about a couple things, and you could be tested on it. I honestly can't remember your quiz if it's going to be on there. So we're going to teach it just in case, but you'll never see these. Maybe you'll see it one other time briefly, maybe like in calculus. A one-to-one function. So there's the definitions and an onto function, so make sure you write those down and understand them. You'll answer them, they make sense. For every input, they have, a pair of just one output from the range. An onto function, the domain, two numbers can go into the same single range number, so it is still a function because it's not like the opposite. If it said this, if we had a 1 and it went to a B and a C, so that input went to two different outputs, that's not a function, so that was not an onto function. Okay, But an onto function, you can see the example down there. And if it's both, that's very unique. Exactly one thing goes to exactly one of the other. It's both an one-to-one and an onto, so that's just very specific. Again, you won't use these much probably ever again outside of this class, so I wouldn't worry too much about it. If it shows up on your test, I might even excuse it if it ends up being something you guys miss a lot, just because it's really not important. Domain and range of functions. So we talked about domain and range. So state the domain and range of each relation. So I'm going to do this first one, and then it says, is it one-to-one, onto, both, or neither? Okay. So state the domain. First off, I don't like when graphs are not labeled like this, so it's kind of driving me crazy. If a graph is ever not labeled, you can assume each little dash there to be 1. Okay. So if that's the case, then we'd start over here. That's at -4. Over here we go up to 4 there, 4, and -4. So I don't like that. In fact, I will take off points when you guys graph things if they're not labeled. Oh, and I even labeled that incorrectly. Here, this is not -4, that's -3. Like, see how it just drives me crazy. Don't do that. Alright. So if I'm looking at this, I have the domain is the x value. So that's my horizontal axis. That's my inputs when I'm putting into a function. I get a -3. I have a -2. Actually, I have 2 points at -2. So it is not a function, because if I drew a vertical line here, I'd hit those 2 points. Okay, but that only counts as one domain value. I have -1, I have 0, I have 1, I don't have a 2, I have a 3, and I have a 4. So that would be, I'd state my domain like that. Okay, my range would be the y value. So I'm going to start down at the bottom of my y values, and I'm going to erase this line so I can see all my points. So I go down to -3, okay, and then I have -2 points, 2 points at -2. Okay, that's a horizontal line. That's okay. We can have functions that horizontal lines hit the same. That's not a big deal. We have a 1, we have a 2, and we have a 4. Okay, is this one-to-one? Meaning, does each value correspond? Well, no. It's not a function, so it can't be one-to-one or onto. It has to be a function to be both of those. So we can say no to, it's neither of those. Okay. Alright, you give this a try, hit pause, state the domain and range. Is it a function? Is it one-to-one? Onto, both, or neither? Hit pause. Okay. So this one, if you look at this, for every input, there is at most one output. So it is a function. Okay. So we will have to test to see if it's one-to-one, onto, or both. State the domain. The domain is pretty much already stated for us there. It's -3, -2, -1, 0, 1. And then the range is 0, 2, 4, 6, 8. Okay. Is it one-to-one? Well, because both -1 and 1 both go to 6, it is not one-to-one. Okay? But it is an onto. So each range, oh no, it's not, because the 8 doesn't have anything on there. So no, it's not onto. So it is just one-to-one. Sorry about that. The 8 doesn't have anything, so it's not onto. Okay, like I said, I'm really not worried about those two things. I think they're pointless pieces of information. Discrete versus continuous. Okay, so discrete, you guys have heard of that before. That would be if we had a graph. Maybe it's a linear pattern, but it goes up with dots like this. That's discrete. There's points. They're not connected. They're individual points. A real life situation would be people. You can't have a half a person. Okay? So that doesn't work. Versus continuous would be if we had that same thing, but it was a line. Right? Maybe that's your bank account. Hopefully your bank account's going up like this one line is. Okay? We can have, you know, half a dollar. We can have cents. You can even really get into, I mean, if you go to the gas pump, you can see what your taxes charge. They go beyond a penny. You can technically charge, and then they just round up when they actually give you what you owe. But so that would be a continuous relationship. You can have halves. You can have thirds. You can have 0.01s, right? So that is a continuous relation versus a discrete relation. Okay, graphing relations. The easiest way to graph a relation is just to make a table. I always go from -5 to 5. I'm just going to make it a little bit smaller and just go from -3. So my x values and my y values. My x values, I just go, like I said, I usually go -5 to 5, but since I don't want to keep you here all afternoon or evening or whenever you're watching this, I will just make it from -3 to 3. So if I plug this in, I would go y, I'm looking for my y, equals -3 squared plus 1. Okay, -3 squared is -3 times -3, which is 9 plus 1 is 10. So I put my 10 here. Okay, and then I'd do y equals -2 squared plus 1 equals, okay, so -2 squared is -2 times -2, which is +4 plus 1 is 5. So we get a 5 there. Okay, I'm not going to write the rest down, I'm just going to talk through it. -1 squared is -1 times -1, which is 1, plus 1 is 2. 0 squared is 0 plus 1 is 1. 1 squared is 1 plus 1 is 2. 2 squared is 4 plus 1 is 5. 3 squared is 9 plus 1 is 10. Okay, so then I take this and I graph it. I need my graph to go up to 10 on my y-axis. Needs to go to -3 and 3. So -3 is 10. 2, be halfway up there would be 5. Ooh, -1 is 2, so it'd be about there. 0 is 1, 2, 5, 10. This makes the shape, oops, I missed a little. It's something like that, sorry. Drawing with my finger here is not very accurate. Yeah, it makes a shape there. Maybe you know what the shape is called because you see that that is a second degree polynomial is what we call that by the squared. That makes a parabola. Okay, it says determine the domain and range. Alright, is there any number that you cannot square? The answer is no. You can square any number. It doesn't matter what it is. So the domain is all real numbers. So domain, all real numbers. Or you could say, it is -infinity to +infinity. So that's how else you could represent it. The range, okay, if we look at this graph, how far up and how far down does this go? Remember, range is the y values. Well, if I look at this, doesn't matter what values I put in, I'm never going to go under this line. The lowest it got down to, if I look at my graph, is that 1. So the range would be y is greater than or equal to 1. Alright? Or you might write it like this. 1, comma, infinity. That just says it's going from 1 to infinity. Okay, those are little brackets. Sorry they're so bad, but that's what this is a bracket, this is a bracket, that's a bracket, that's a bracket. Sorry, they're supposed to look like, I don't know how they're supposed to look like that if you draw them really slow, but I'm really bad at drawing them, so sorry. You'll get used to my handwriting. Okay, So I want you to try now, determine the domain and range of the graph y equals 2x plus 1. Hit pause. Okay, so like I said, the easiest way for any relation, if you don't know how to graph it, is to just make a table. So again, if we just go from -3, -2, -1, 0, 1, 2, 3, if we find out all these numbers, this is our x's and our y's. Okay, -3 times 2 is -6 minus 1 is -7. -2 times 2 is -4 minus 1 is -5. 2 times -1 is -2 minus 1 is -3. 2 times 0 is 0 minus 1 is -1. 2 times 1 is 2 minus 1 is 1. 2 times 2 is 4 minus 1 is 3. 2 times, I haven't written any of these out, so I'll maybe write this last one out. 2 times 3, so I just put that x value in place of the x in the equation, minus 1, that's y equals 6 minus 1, which is 5. You might have seen a pattern there. Some of you even recognize that this is in slope-intercept form. Okay, we need to go from, well, let's see, let's just go from -10 up to, we'll say that's 7 up there, that's 5 right there, and again -3 to 3. See if I can split this up a little bit more so we can really get some better visual. Okay, -3, -7 here, -2, -5, -1, -3, 0, 1, 1, 1, 2, 3, 3, 5. Okay, so that, and we can put numbers in between. Can I put -2.5 in? Yes, I could. So this we would connect with a line, just like we did above with a parabola. Okay, so there's our graph. Determine the domain and range. Well, domain would be the x value, so what can I input into this function? Is there anything that I can't put into this function? No, I can put everything in. Another way to think of it, how far to the left does this graph go? Well, the arrow shows it goes forever to the left and forever to the right. Okay, so if I look at that, the domain, we said is all real numbers. I think that's easier. Some people will, like I said before, say that they'll do the little brackets, say -infinity to infinity. For those of you that go on to calculus, you'll usually see it with the brackets. The range, if we look at this, it also goes down. That line keeps going down, so an arrow says that goes down forever, and the arrow up says it goes up forever. So again, the range is the y values. Y is up and down, vertical. Alright, so we could also say range is all real numbers or -infinity to +infinity. Okay, so hopefully you got that yourself. Okay, independent versus dependent variables. We talked about that already. Independent variables are your x variables or your inputs into a function. Okay, the dependent variable is the y values, or a lot of those equations where y equals something. Well, in order to find what y is equal to, it depends on what we put in for x. So that's why it's the dependent variable. And especially when we get into function notation where we say f of x, well, you have to put, in order to find out what the function, what the answer of this part of the function is, you have to put something into it. So f of x is the same thing as y. It's more specific, so we can have f of x equals, like before we had that 2x minus 1 function, which is the same thing as the 2x minus 1. We're just getting more specific with function notation. So f of x is more specific. We're talking about the function x, or the function f. So let's say we were dealing with multiple functions. It'd be nice to call this, maybe this function we call f, and then another function we call g and another function we call h. So when you're dealing with multiple functions, so that you can keep track of them easier, we use different letters to represent them. So it's just an easier way to keep track of multiple functions. Alright, but again, like we said here, to remember it with independent versus dependent variables, x is always your independent variable. We can put anything in there, it doesn't depend on a y. Alright, but the y value, or the f of x value, that's the dependent variable, because it depends on what you put in for x. That will give you your y value, or your f of x value. So that is independent versus dependent. That's a little bit about function notation. Another example of function notation is in physics. They'll use, like for a velocity function, they'll say v, for velocity they'll say v of t. Okay, that means velocity, which depends on time. Velocity depends on time, v of t. So you'd say that. And the way you say all these functions when they're in function notation is the first letter and then of whatever is inside the parentheses. So f of x, v of t, maybe I had the q of t function, q of t. So a lot of people, if you say it wrong, then you're going to say qt. And maybe that's what you say to your girlfriend, but that's not how we talk about q of t. Alright? Okay. Sorry, bad joke. Evaluate a function. So here we're just going to look at this. If we have the function g of x equals 0.5 x squared plus 3.5, find g of 2.8. Okay, all you do is put 2.8 in place of the x. So that's g of 2.8 equals 0.5, and then in place of the x we put 2.8. Okay, we're going to square that number plus 3.5. Once you do that, then it's all about PEMDAS. So what do you have to do first? You have to do exponents first. So g of 2.8 equals, so 2.8 squared is 7.84. And then we multiply those. G of 2.8 equals 0.5 times 7.84 is 3.92 plus 3.5. And finally, g of 2.8 equals, let's see, 3 and 3 is 6. We're going to have to go up one, so 7.42. Okay, you have a bit more of a challenge because I want you to try this one. Find what is g of 4a. Give that a shot. Last problem. Okay, so g of 4a. Again, in place of the x, we're just going to put 4a. Okay, because it says 0.5 times x squared up here. Alright, so we just put in place of that x squared, we substituted in 4a plus 3.5. Okay, so this one's a little bit harder. G of 4a is equal to, if we square 4, we get 16. If we square a, we get a squared plus 3.5. Okay, and that is equal to half of 16a squared. Well, if we have 16a squared values, then half of that would be 8a squared values. 8a squared plus 3.5. And then 3.5 does not have an a squared with it, so we can't compare the two. We can't combine those two because they're not like terms. So keep them separate. That really is our final answer, so we should rewrite it as g of 4a. Remember, say that g of 4a, g of and whatever's in the parentheses, equals 8 a squared plus 3.5. That's our answer. That's it for this video. There was a lot, I know, kind of a longer video. I'm sorry about that, but bring in any questions. Thanks.